Welcome to DC Circuits Review Part 2, and today we're going to talk about a very somewhat simple device that tends to cause some troubles if you don't understand it and the circuit it's in, and that is a switch. Now this switch is shown to be opened. That means that if we take the resistance and measure it across the switch, it theoretically will approach infinity ohms. Realistically, it's going to leak a little bit, but for all practical purposes, we can figure that it completely interrupts continuity in the circuit. Secondly, we have a closed switch. This means that we have a path through the switch. We could say that the resistance of the switch ideally approaches 0 ohms. Actually, it does not. If you look up a given switch in a data sheet, you will find that it has some resistance associated with it, and this will give us continuity through the circuit, assuming that there's no other device which can interrupt the circuit flow. Now, that may seem pretty simple, but let's take a look at some circuits. This is called a high side switch, and this is the easy one, and unfortunately it's not used as much in the electronics industry as a low side switch. So let's review this. We have a 24 volt source, a switch, 48 ohm load in both cases, and in this case we see that the switch is open. So we want to measure V relative to ground. Now remember, this is a doubly subscripted variable. Red meter lead goes here, black meter lead goes here, and what we find is that V out is equal to 0 volts. We also find that the voltage across the 48 ohm resistor, the voltage drop, is also equal to 0 volts, and the reason is that I equals 0, and from Ohm's law, V equals I times R, and 0 times 48 ohms is going to be 0 volts. Now we have the same circuit with the switch closed. Conventional current now flows in this direction, and if we're measuring V, as you can see, we're connected to the 24 volt source, and we would measure 24 volts relative to ground. The voltage drop across the 48 ohm resistor would also be 24 volts, and if we were to find the power in the circuit using V squared over R, we would find that to be 12 watts. In this case, the power across the circuit is going to be 0, if you will, because I squared R, 0 squared times 48, would be 0. Notice that I used two different power equations when I did that analysis. Now for the low side switch. This is where things can be confusing because a lot of the industry uses low side switches. So in a low side switch, we're going to start out with basically the same circuit, 24 volts, 48 ohms, but the switch is going to sit between the resistor and ground. And this is our point V that we're interested in measuring. Now if the switch is open, the current flow through this here, I, is equal to 0 amperes. That means that the voltage drop across the 48 ohm resistor is going to be 0 volts. There's no current flowing through it. Now if we have a 0 volt drop across the resistor, what that means is one side of the resistor is the same voltage as the other side. The drop is 0. Since this side is connected to 24 volts, what we see is that the test point V, if we were to measure it, would be 24 volts. The voltage across the 48 ohm resistor, if we were to measure it, would be 0 volts. Why? No current flowing through it. The power in the circuit would be 0 because I squared R with 0 squared times the resistance would produce 0 watts. Same circuit, close the switch, conventional current now flows. We have a voltage drop across the 48 ohm resistor, plus to minus, and now what we'll see is that V here is equal to 0 volts. Why? It's connected by a short circuit per se, the closed switch to ground. The voltage across the 48 ohm resistor, however, is going to be 24 volts. Current flowing through this now produces that drop. The power dissipated in this case would be 12 watts as it was above. Now the confusing part about this is that in this circuit we have a voltage output. And typically what a student would like to do would call this circuit on. It's not. So when you get into low side switches, you have to be very careful as to what you're analyzing. And a good example with this would be a microprocessor port feeding a light emitting diode. Typically the diode, one side of it would be connected to the positive supply and the port pin would go low to turn on the light emitting diode. So high and low side switches are important, and we're going to see a lot of these in field effect transistors topic coming up in the future. Now let's take a circuit which is a little bit different. Here we have two different power supplies, and when you see anything like this, the first thing you ask yourself, are these aiding or opposing? And since we're minus the plus, these are series aiding, and we can conclude that if we put our voltmeter across this, negative lead here, positive here, lead here, we would see 20 volts. Now the current's going to be flowing in this direction, plus to minus, as we would expect through the load, and what we know is that the voltage drops across these resistors has to equal 20 volts. So to find out what the voltage drop, DROP, and remember this does not NOT reference ground. We would just use voltage divider again, 20 volts total, 48 volts in the numerator. Our total in the denominator gives us 16 volts across the resistor. Doing likewise, and there are other ways of doing this, but I'm going to do it the long way and explain both, is that we have 20 volts, 12 is in the numerator, and our total is in the denominator, so we get a 4 volt drop across this. We don't know what it is relative to ground. We don't know yet, that is. So the language that you need to use in here, and what's super important, is that you show your current flow and show your polarities. Always a good idea. And it's such a good idea that even SpongeBob agrees with it. He says, always do that. You're less likely to make a mistake. So the language you want to use is the key to solving this guy. Since the bottom of the 48 ohm resistor is 16 volts more negative than the top. 16 volts more negative to the top. And we know that the top is connected to plus 12 volts. So we have to know one end of the resistor voltage relative to ground. Therefore, it's just a matter of taking the 12 volts that we have here, subtracting from it the 16 volt drop across the resistor, which gives us negative 4 volts for V out. Remembering that V out is a doubly subscripted variable, and the second subscript is ground. If we were to do the same thing, and I did not include it on this sheet, we would say that this side of the resistor for the 12 ohms is 4 volts more positive than this side of the resistor. And since this side of the resistor is 8 volts negative with respect to ground, this would be 4 volts more positive, or the voltage here would be negative 4 volts. The same as what we did before. Now we could find this drop in a different way. We don't have to use voltage divider. We could just simply say that, well, if I have 20 here and 16 here, according to Kirchhoff, I have to have 4 here. Now, which way do you want to use? Well, it's kind of up to you. If I misfire on this equation, I get a wrong answer if I subtract this voltage from 12. If I use voltage divider twice, a mistake up here will not affect this answer. And then if I elect to do a check, always a good idea, 4 plus 16 has to equal 20. It will not, and I'll ask the question, how come, and then go looking for a problem. Now, when it comes to that, some students plug and chug in calculators. And that's not a good idea. And the best example I can give is when I was adjuncting at Tri-C. It was an Electronics 1 equivalent course. A student correctly calculated the gain of a transistor amplifier to be negative 66, which means It's 66 times larger, that is the output, but it's inverted. The sine wave is going in the other polarity first. He built a lab, measured -3, and turned the lab in. No bells went off as to 66 theoretical, 3 measured. Nothing. Write it down, turn it in, go home. So this student really kind of hurt himself. And all he had to do was ask a question. He made a wiring error. Probably something real simple, but just didn't care. So when we, talking about the faculty in general, do instruction, we want students to understand the theory behind it and know what makes sense. If this voltage came out to be 22 volts, how could that be with a source of 20? That's a red flag. Now if there's inductors and capacitors in a circuit in a switching mode, that is possible, but not in a pure resistance. So what I'm saying here is always use common sense. Does your answer make sense? And that'll help you score higher grades on tests. And this concludes Part B.